In this session, I would be talking about an important measure of the shape of the distribution. Shape of the distribution of the data, right? So that is that shape which is going to measure whether my data is more and more symmetric, whether the distribution of my data is more and more symmetric, or is it more and more skewed to one side or the other, right? Is it skewed to the left or is it skewed to the right? So we are trying to measure, we are trying to arrive at a measure which tells about the shape of the data or the amount of skewness that is present in the data, whether the data set data distribution is more symmetric or skewed to one of the sides. Typically, we have seen when we are going with a plot of the histogram, we would see whether the histogram is more and more symmetric. Is it more looking like something like this? Or is it like the peak is here, but I have the values coming more like this? Or is it like the peak is here and the values are somewhere like this? So when I'm saying that the histogram is coming more like this, where the peak is more or less somewhere towards the right and the values are like this, or probably is it like the peak is more or less at the center and the values are gradually falling. So whatever is the shape, that is what to a large extent the approximation of the shape can come through histogram. Even your stem and leaf plot would have given you a similar kind of a diagram, or even your dot plot would have given you a similar kind of a shape. So approximate shape you can very well get through any of these distribution. And a quick look of any of these diagrams will on an overall scale give you whether your data is more or less fairly symmetrical, or is it more and more skewed to the right, which is what we call as positively skewed, or is it more and more skewed towards the left, which we call as negatively skewed. So typically negatively skewed or left skewed data will look, the graph of the histogram of it will look more like this. Positively skewed or right skewed kind of a data, the histogram or stem and leaf plots will look more like this. And for symmetrical data, the histogram will look more or less like this. Right? Generally, the proper shape will come if the observations are more. Just with 10 observations, very small set of observations, probably the skewness cannot come that significantly. But if I go with a large data set, the skewness can quite comfortably be seen in the data. Let's look at a quick data set. Okay, let's look at some data set values. Let's say 30 values are there in my data set, right? I would like to plot the frequency distribution for this. Let me see the frequency distribution. So I know that the values probably what is the minimum value here? The minimum value appears to be 10. And what is the maximum value in this data? The maximum value appears to be 20. So what I'll do is I'll take a simple frequency distribution. I'll take it as a discrete itself, right, up to 20. And I am doing a count if kind of a function to find out what is the frequency of occurrence of each of the observations. So 10 has come only once, some of them have come twice, thrice, whatever it is. Now I can very well plot the histogram with this kind of a data. Okay, this is the kind of a histogram that has come out from this data, right? probably I can very well reduce the reduce the gap, right? I'll eliminate the gap from this. So probably this is what is my histogram looking like. And on a broad shape, I see that it is slightly negatively skewed because the peak is somewhere here. And after that, it looks like some kind of a fall. So it looks to some extent there is a kind of a negative skewness. So this is a typical histogram giving me some meaning about the skewness that is present. So this data may not be symmetric, right? But we could see that it is more and more negatively skewed kind of a data, because we have seen that the definition of a negatively skewed data is nothing but I see the shape more coming like this. I see some small frequencies towards the left and some high frequencies towards the right. So that is what I'm observing in this graph. So approximately I can say that this graph is negatively skewed. But if I really want to come out with a proper measure for skewness, so a proper measure for skewness is nothing but the third moment about the mean, right? Third moment about the mean. So which means from each observation, subtract the mean, cube it, add it, and divide it by the n. That is what is the third moment about the mean. So let's try that with the data. Right, we know the mean of this particular data, the mean which is coming out with the average formula, the mean of this particular data is around 15.76. This is the mean of the data. Now what is that I have to do? I have to subtract every observation, the mean from it. I'm subtracting the mean and I'm cubing it. Okay, I've subtracted the mean and I cubed it. So this I'm going to sum up. The sum of that is going to come out to, the sum of those values has come out to around minus 209. And if I have to find out the skewness that is present in the data, I'm dividing this 209 by the total observations, which is 25. So giving me that my skewness is minus 8.39. And negative is an indication that my data is negatively skewed. Now, this way, the skewness does not have, the skewness that I'm finding out in this way, one, it has units. It is affected by the units. And two, there are no boundaries to it, so I cannot really define which is high and which is low. So because of the units, this gets very much biased. The same thing if I take it in terms of 20 kilometers, then the definition could be different. The value could be different. And if I take it as 20,000 meters, then the value of the skewness could be different. That is where the interpretation will change, which should not. That's the reason we come out with another important measure on the top of it called as coefficient of skewness, which is nothing but it's a scaled version. We'll find out the skewness, but we scale this moment by dividing it by the second order moment about the mean, which is nothing but the variance. We know, right? Second order moment about the mean, I'm raising it to the power 3 by 2. Second order moment about the mean is nothing but my variance. So the second order moment about the mean, I raise it to the power of 3 by 2. I divide by that. Okay. Let's find out the second order moment about the mean. So which means from every observation, I have to subtract the mean and square it. right? Because I want the second order moment about the mean. So I am summing all the squares of deviations from the mean. This I am dividing it by 25. This is the second order moment about the mean. And this I am raising it to the power 3 by 2, which is 1.5, where I am getting 25.28. So based on this, I am getting my coefficient of skewness, which is nothing but the skewness which I got in the earlier case divided by the second order moment to the power 3 by 2. Skewness is coming out as minus 0.332. So we have even a formula called skew in Excel, which will give me more or less a similar kind of a value. So this is a way out where I am measuring the skewness. Here basically instead of dividing by n, there could have been a division by how many observations are there? Let me just look at it. Here the number of observations is 30, not 25. Right? So even the skewness here is a division by 30. And here also the division should be by 30. Right? And the point here is it could have been divided by n minus 1 for the calculation of variance, right? Or probably 30 itself. So a slight difference in the way the calculations are done, but otherwise the skewness is a straightforward mechanism. We are finding out the deviation, the third order moment about the mean, and we are dividing it by the second order moment about the mean to raise to the power of 3 by 2. And by doing this, we are eliminating the units. We now see the numerator is also a third order one and the denominator is also a third order one. So we generally don't have units, only the sign matters. Negative means I can say that my data is negatively skewed. Positive means my data is positively skewed. Otherwise, I can say that my data is more or less symmetric. So that is the simple way of using or measuring the skewness or the shape of the distribution. Then another important graph or technique that really helps us in understanding the shape of the data is the box plot, otherwise called as a 5-measure summary. What we do as a part of the 5-measure summary is we use the quartiles Q1, Q2, Q3 and along with the extreme values, the minimum and the maximum. So these 5 values are helpful in the display of the box plot. The summarization using these 5 values is what we call as a box plot. Typically, the box plot looks like this. We have a box or a rectangle. It could be horizontal or a vertical way. Different tools give the different way. This is Q1. This is Q3. The quartile 1, quartile 3 are the extremes of the box. Somewhere in the middle there is Q2, which is the median. So these 3 are shown here. And there are lines that are drawn from here to here. Probably there is a minimum value. This side there is a maximum value. To the extreme values it is drawn and these lines are typically called as whiskers. So that's the reason we call these kind of plots as box and whisker plot. Right? And in some tools, statistical tools where the box plots are plotted, they identify some kind of stars in the data, which they talk about as outliers. Especially with the statistical tools, they identify the outliers as the stars. Some kind of observations which are detached from the other part of the data, which are very extreme from the rest of the values. they identify using stars, which are typically called as your extreme values or outliers in the data. But the good thing about the box plot, one, there is a median, which is a measure of central tendency. IQR is a measure of dispersion. And the shape, relative symmetry, whether it is more skewed towards the left or skewed towards the right. So even a measure of a shape or the symmetry of the distribution. All the three measures of the data are quite comfortably be seen in the box plot. So very important for us to understand the box plot, because with the tools, this box plots even go a little bit forward in terms of we understanding the outliers that are present in the data as well. So understanding the three dimensions, which are the location, the dispersion, and the shape of the distribution, will definitely help us in terms of understanding the patterns in the data more and more effectively. All right. So thanks a lot for listening to this session. Thank you very much.